Hi everyone. In section 10.4, we'll talk about hyperbolas. Really, on a final exam, I would only require people to know two things about hyperbolas. And your homework on 10.4, notice those were both additional problems. They're optional. But even though many of these ideas in 10.4 are optional, it's good to go over them, and they're good ideas. All right. So remember, there are four types of conic sections: circles, ellipses, parabolas, and now hyperbolas. And actually, we have seen hyperbolas before. On Desmos, remember the graph of y equals 1 over x. This was a hyperbola, a graph with two branches. In this case, we had branches in quadrants 1 and 3, and this hyperbola had two asymptotes, namely at the x-axis and at the y-axis. In fact, we can think of this as a rotated hyperbola. Y equals 1 over x is a rotated hyperbola. The hyperbolas you normally deal with are either horizontal, like this guy, or vertical, like this guy. And bottom line, these are the only things that I would need people to know for a final. The graph of x squared minus, not plus, like for a circle, x squared minus y squared equals 1, looks like that. It's a horizontal ellipse, opening horizontally. Y squared minus x squared equals 1 is the vertical ellipse, this graph here, which opens vertically. So as far as the final material goes, that's all I need people to know. But let's talk more about hyperbolas. Again, hyperbolas have two branches. It's the only one of the conic sections that has two branches. Here, one branch over here, one branch over here. On the vertical ellipse, one branch opening up, one branch opening down. So either left and right, or up and down in terms of how they open. Now, let's talk briefly about the locus definition of hyperbolas, the geometric definition. So we talked about the locus definitions for circles, ellipses, and parabolas. Now, the locus definition for hyperbolas is similar to the one for ellipses. Remember, the locus definition for an ellipse said that an ellipse consists of the set of all points whose sum of distances from two fixed points, which we call foci, remains the same. The sum of distances remains constant, remains the same for all points on the ellipse. Now for hyperbola, it's similar, but instead of the sum of distances being kept constant, it's the absolute value of the difference of the distances. The absolute value of the difference of the distances. So for example, let's say that we have two foci. We do have two foci. Let's say over here and over here. The two foci are sort of eaten by the two branches. Right? Now let's consider a point on the hyperbola. Let's say this point on this right branch of the hyperbola. Consider the distance from this point to this focus, and also the distance from this point to the further focus over here. Now, the difference between these distances will stay the same for the various points on this branch of the hyperbola. Okay, if you consider this point over here, draw this point over here. All right, consider its distance from both this focus over here and this focus over here. Again, the difference in the distances will remain constant on this branch. We talk about absolute value because if you consider, for example, this point over here, consider this point over here. Okay, it's closer to this focus. Its distance from the other focus is over here. Okay. But again, the absolute value of the differences, the absolute value of the difference of the distances will stay the same. The longer distance minus the shorter distance, that'll stay the same. We talk about absolute value because sometimes the longer distance is to this focus, sometimes it's to this focus. But bottom line, the longer distance minus the smaller distance will stay the same for the points on both branches of the hyperbola. That's the locus definition. Now, what's the reflective property And this has real practical application in the military, in navigation. So let's consider this point over here. What's the reflective property? The reflecting property. So consider this point over here. Now, once again, let me draw the two foci. So I'll draw the two foci again. Let's say the foci are over here and over here. Let's say that we aim a projectile towards this focus over here. We aim a projectile towards this focus over here. But it doesn't make it all the way. It doesn't make it all the way. It hits this hyperbolic surface. And from this point on the hyperbola, it's reflected. And the way it's reflected is that it's then directed towards the other focus. It's directed towards the other focus. So that's the reflecting property of a hyperbola. Okay. Actually, when I was talking about the applications in navigation, that was more towards the locus definition than the reflecting property. Let's go back to the locus definition. Let's go back to the locus definition. What's the application to navigation? All right, so consider a point on the hyperbola. All right, again, we consider the foci over here, one focus over here, one focus over here. All right. Property of hyperbolas, the difference in the distances remains the same. Okay, now what's the application in navigation? And in fact, this is an idea used in LORAN. LORAN, L-O-R-A-N, short for long range navigation. This is a Wikipedia article. Not that I always look to Wikipedia. Okay, was a hyperbolic radio navigation system developed in the United States during World War II. By the way, telescopes use ideas of hyperbolas as well. Now, what's the idea here? Again, if you consider the various points on this branch, this particular branch of the hyperbola, remember, the difference in the distances from the two foci will remain the same. Now, how is this applicable in, say, LORAN or in, say, navigational applications? Okay, let's say that at the two foci, we have tracking stations, all right? And let's say that this tracking station on the right at this focus hears an explosion out at sea 5 milliseconds before this tracking station does. Based on that information, you can model a hyperbolic curve. And basically, based on that information alone, the fact that the tracking station on the right here at this focus heard the explosion 5 milliseconds before this tracking station at the other focus, we know then that the explosion, or we can figure out that the explosion happened somewhere along this hyperbolic branch. Okay, because remember, this hyperbolic branch consists of all points whose difference in distances from the two foci is the same. So that corresponds to the fact that, that this tracking station heard the explosion 5 seconds before this tracking station did. And that's a key application of hyperbolas in navigation, LORAN, okay, tracking explosions. All right. Now, back to the math. I'll erase these here. Back to the math. So this here is the graph of x squared minus y squared equals 1. So this is a horizontal hyperbola. It's a hyperbola that opens to the left and to the right. Okay, now one way that you can tell that it's a horizontal hyperbola is that we have the x squared term over to the left of the minus sign, where the y squared term to the right of the minus sign equals a positive number. And in standard form, we want a 1 there. Okay. Bear in mind, if that's a negative 1, we have to mess with the equation. But if you have x squared minus y squared equals 1, that's a horizontal hyperbola. One way to see that is that if you look for intercepts, all right, the x-intercepts are where y equals 0. So if you plug in y equals 0 and you kill that term, you get x squared equals 1. That means that x equals 1 or negative 1. And we get 2 x-intercepts. But what about y-intercepts? What if we let x equal to 0 and get y-intercepts? The opposite of y squared equals 1. There are no real solutions for y. So notice this hyperbola has no y-intercepts over here. The asymptotes, by the way, the lines that these branches approach in the long run, we have y equals x over here, and y equals the opposite of x over here. Desmos verifies that. So looking over here, here's a graph of x squared minus y squared equals 1. It's a horizontal hyperbola. Notice we have 2 x-intercepts at 1, 0, and at negative 1, 0. Okay. And in fact, these are the vertices of the hyperbola. They're like turning points. These are the vertices of the hyperbola. Y equals x is one line that the hyperbola approaches in the long run. Y equals the opposite of x is another line that the hyperbola approaches. They form an x. The two asymptotes form an x that go through the center of the hyperbola, which is at the origin. The center is in between the two vertices. In a way, it's outside the hyperbola. Remember, an ellipse sort of contains its center. A hyperbola does not contain its center. Okay, these two branches do not eat the center here. Now, over here, y squared minus x squared equals 1. All right, here we have a vertical hyperbola that opens up and down. Again, in this class, we're not going to rotate these things 45 degrees or anything, right? That's from Math 151. Now, we know it's a vertical hyperbola because this equation is of the form, okay, the y squared term is to the left of the minus sign, okay? The x squared term is to the right of the minus sign, equals a positive number here. We want a positive 1 here for standard form. Similarly to before, notice that the intercepts, we have intercepts of one type but not the other. Okay, we have y-intercepts. When you set x equal to 0, y squared equals 1, so y equals positive 1 or negative 1. Here are the y-intercepts. They're also the vertices of the hyperbola. But if we try to look for x-intercepts, when we set y equal to 0, well, this has no solution for x. So there are no x-intercepts. The asymptotes are the same as before. Y equals x and y equals the opposite of x. Right. So I'm flashing the horizontal hyperbola here, x squared minus y squared equals 1. Here, this is y squared minus x squared equals 1. It's a vertical hyperbola, but we have the same asymptotes, the same x representing the two asymptotes. The intercepts are y-intercepts this time, vertices 0, 1 and 0, negative 1. Putting them all together, both this horizontal hyperbola and the vertical hyperbola have the same asymptotes. It's a very nice picture here. If you want to put in all the vertices, 1, 0 and negative 1, 0. Big happy family. These two hyperbolas, the common asymptotes, and the intercepts or vertices. All right. Now, again, I only required you for the final to know the graphs of x squared minus y squared equals 1, a horizontal hyperbola, and y squared minus x squared equals 1, a vertical hyperbola. In the next video, a bunch of optional notes, but some interesting extensions. Next time.